Wow.
So
I've never seen anyone do that.
we've been doing, right? We've been building these confidence intervals. And it kind of all is based off of this knowledge that it doesn't matter if we've got kind of this normally distributed variable X or how it starts out distributed, it could have any distribution that, or we're looking at a proportion, which we said is kind of unique case of the sample mean where we had a 1-0 variable. That our sample statistics, as long as we can get a sample size over 30, will be centered around, or the mean of those sample means will be whatever that population mean is. And if we're looking at proportions, it's just going to be whatever that population proportion is. We then said for any value from this distribution, we can turn it into a z value by doing the following. Taking that value, subtracting the mean of that statistic. So the mean of the sample mean is just the population mean. And then we'll divide by the standard deviation of that statistic, which we know is just the square root of the variance of the data we sampled from over our sample size. And the only thing that changes for this sample proportion or for sample proportions, we're not looking at means, we're not looking at proportions. And the standard deviation of our sample proportions look like that, right? Because when you the variance for our proportions follows p times 1 minus p, we don't actually have to calculate. All right, so this was the idea that kind of we related to the binomial. We're looking for the number of successes. We had this variance equation that always gave us variance. Well, now we just want the proportion of successes. So there was just no multiplication by n. Does that answer your question?
What's the X?
X bar,
Yeah,
that's our sample mean.
so,
So these are going to be like different cutoff values in practice, right? Whatever value you see from your sample mean, that's kind of what you're trying to figure out. How many standard deviations was that value away from the true population statistic?
what if you're only giving one?
You have a specific homework question, you can ask me after class,
Okay.
but you're going to have to be given what that population mean is, and you're going to have a sample mean cutoff value. Like that's the old, otherwise there's, I mean, unless it's asking you for something like, you know, gives you everything else and you've got to back out what that cutoff value is. But that's kind of what we would call like the inverse process. I don't think I have any on there with a sample mean there like that. You might have some on there that's just regular population data, right? Where you have to do the inverse. You know, the area that you want in the tail, and you have to work backwards to find out what cutoff value that's going to be. So this is a little bit of a roadmap for what we're going to talk about today, which is we've built confidence intervals for both using our sample mean for where that true population mean is. We've used our sample proportion to build a confidence interval for the true population proportion is. I said something that's kind of hokey in all of this is we thought about how we were doing confidence intervals before, where this guy right here was representing that standard deviation of our sample means. So I'm trying to build this confidence interval for where the true population mean is because I can't observe it. Well, how in the world do I have the population variance? I said, well, maybe there's this machinery, you know, some process on machinery, and then through chemistry or physics, I can figure out exactly what that variation would be. But more likely than not, right, if I'm thinking about something like, I don't know, measuring income, I'm going to have no idea what the population variance is for income. And if I can't observe the population data, what am I going to use? Well, just like we're using the sample mean for the best guess of where this population mean is, we're going to use our sample variance for the best guess of what that population variance is. Now, what else is going to change is that when we're calculating this sample variance, remember what was the difference between the population and sample variance? Instead of dividing by n, we divided by, going back a ways. So the only difference between calculating the population and sample variance, we said if it's population data, we have to divide the sum of the squared, sum of the deviations from the mean squared. We divide that by n. If it was a sample, we divided by n minus 1. So dividing by n minus 1 was always kind of erring on the side of caution. We were dividing by a slightly smaller number, so that inflated our variance. Okay. So depending on the size of our sample, that's going to change how much that sample variance, even if I did have the population data and treat it as a sample, that difference between divided by n and n minus 1 is going to be different depending on the sample size. If I divide by 1 instead of 2, that's going to cause a much bigger difference than if I divide by 999 instead of 1,000, right? And so every time we're kind of looking at different sample sizes, the smaller the sample, kind of the more inflated that sample variance is going to be, or the more that we're going to be like erring on the side of caution by overinflating that variance. So we're going to have this thing that we're going to be concerned with, which is, okay, if I'm only using a sample variance, then when I try to turn any sample mean value into a standard normal a standard normally distributed value z, right? That's what we said z was. Well, we no longer are using our population variance. And as a result, we kind of use slightly different notation here, which is, this is still the standard deviation of my sample means, but writing as an S indicates I'm calculating it using sample data or using the sample variance. And because I'm doing that, and I'm dividing by n minus 1, I know that I'm kind of overinflating kind of what that variance is. So when I think I'm calculating a z value, I'm actually not. It's not going to be standard normally distributed. So when we're converting these now into what we'll call t values, right? So they're just still the number of standard deviations away from that mean. So it's the number of standard deviations away from that mean, that whatever cutoff value or whatever sample mean we see is, right? It's just that it's going to come from a different distribution, right? Because we know it's overinflated, it's going to be, trying to think about if I tried to overlay these. So if this is my standard normal distribution, right? These t values will be slightly more spread out because the variance, the sample variance divided by n minus 1 will always be a little bit larger, right? So a larger variance means we kind of have this more spread out or this flatter distribution. So this creates a problem because now when we go to look up that z value, it's no longer a z value, the t value, right? But it's the same process. We're just going to have to use a different distribution. Essentially, you can think about it, that standard normal table was integrating that probability mass function I showed you a long time ago and said, don't worry about it, we're not going to have to integrate this function. It's a very similar function for the student t. It just has it's a little bit different of a formula. So when I integrate it, I'm going to be coming up with slightly different values. So the whole process is going to stay the same. I'm going to calculate my sample variance, my sample mean, and find my sample size from some data set, or that's going to be given to me if we're thinking about this in terms of like a problem. Excuse me. And before, when we were trying to look up that z value that gave us alpha over 2 on either side of our confidence interval, we're still doing that. It's just that it's no longer a z value. It's coming from not the standard normal distribution, but what we'll call these student t distributions. Okay. Now, if I can get this going here, I kind of already mentioned that depending on what the sample size is, that sample variance will be a little bit more overinflated, right? So there's not one student t distribution, there's several of them, right? Every single sample size will have its own degree of freedom, right? Or what we'll call a degree of freedom, right? So standard normal distribution was one distribution. Student t distributions are a bunch of distributions that are all normally distributed, just not quite standard normally distributed. Okay. So we're going to have to use a different table. And the way we identify which student t distribution we're going to use is just based off of the sample size minus 1. Okay. Kind of lining up with that fact that we're dividing by n minus 1 now. Okay. So it's still going to be symmetric. It's going to be symmetric around 0. So that's same as the standard normal distribution. It's just going to be a little bit more spread out. Right? Now, the higher the sample size we get, the closer and closer it gets to being standard normally distributed. But for really low sample sizes, that student t distribution might be a lot more spread out. Okay? So we kind of think about what this is going to look like. So again, I mentioned here, if you get a sample size over 100, it's almost indistinguishable from the standard normal. So a lot of the times we'll do in practice is if I do get a large enough sample size, I can use the standard normal as opposed to student t because I can such a close approximation, like out to the 4th decimal, that I'm basically finding the same values. But we're going to deal with small sample sizes so we get an idea about how we use the student t distribution. So we think about this, I kind of already had this in the board, but relative to the standard normal distribution, if I have to use a student t distribution, it's going to be a little bit flatter. And then if I had a smaller sample size, like 5, right, it's gonna be even more flat. Well, what's the problem here? And I'll draw this out on the board because I think we kind of show this in the slides, but I have a difficulty kind of putting things on slides sometimes. It's easier to freehand draw it. So let's say here's my standard normal distribution. And here's a student t distribution. I don't know, we'll say the degrees of freedom is 20. Try to kind of match it to the slides here. So it's a little bit flatter. If I want to go 1.96 standard deviations away from the mean, or a z value of 1.96, if I look that up in the table, it'll tell me the area to the left. If I want to think about just the area to the right here, it would be 1 minus that. We kind of hopefully, I don't know, from other confidence interval examples, whenever we look this up, we were always kind of getting 0.025 there in the tail. Well, the problem is if I try to use that same cutoff value, that same number of standard deviations away, I'm no longer going to be guaranteed to have 0.025 in the tail. I've now got a much larger probability. Right? So this is no longer going to match up to a 95% confidence interval because there's now an increased chance I see something that's 1.96 standard deviations away. So I can't keep using those same values I would have found for my standard normal distribution because now those won't match up with that desired alpha over 2 I want in the tail. Here from the student t distribution, what's going to have to be true about the t value I would need relative to this z value in order to get there to be 0.025 in the tail. So if I think about the area underneath my curve, this green curve, the student t distribution, and to the right of 1.96, I know that area is greater than 0.025. So if I want to decrease that area down to that desired alpha divided by 2 of 0.025, what am I going to have to do? Yeah, I'm going to have to choose something, I drew this really extreme. So I might have to go all the way out here so that I can kind of get alpha over 2 on that right side. So when we're looking up these student t values, for the same level of confidence, right? The same alpha divided by 2 area in the tail, I'm going to have to be using higher number of standard deviations away, or my t values will always be higher than those standard normal values that we found. Okay. So I'll kind of have this here. And it's like I said, I think it's easier to draw shorthand. You can kind of see the area under this black curve, which is the standard normal. If that's 0.025, well, the area under the green and the blue curve is going to be much larger than that, right? So I've got to choose. In fact, if we look at those, and I'll show you the student table in a second, if we were to look at that same 1.96 value, the areas are quite a bit larger than 0.025. So these definitely are going to correspond to the confidence intervals or confidence levels that we want. So I'll pull up actually, I don't know why I even have this in the slides, but oh, I guess that's why. But I'll show you the actual student t table that's up on Canvas that you'll kind of be using as we move forward. Right? So it's a little bit different than the standard normal in a couple ways. So the first way is that the standard normal was always looking at the area to the left, right? Excuse me. For the student t table, it's going to be thinking about the area in that upper right tail, right? So it kind of reminds you of that up here. But now that's okay because if I know that, for instance, I don't know, I'm just going to choose an arbitrary number. Let's say it's 2.23, and I tell you the area to the right of that, I find from that table is, I don't know, 0.042. Right? Well, if I wanted the area in the left, this is a symmetric distribution. So I know that the area to the left of negative 2.23 would be that same 0.042. So even though I only have the positive values, the right side of this distribution, because it's symmetric, I can still find the areas in those left tails if that's what I need to do. Now, in practice for confidence intervals, we said that positive and negative are already built into our confidence interval equation. So the student t table actually makes it a little bit easier because when I look up alpha over 2, it'll just tell me the positive t value that I need to plug in. We said if this is the number of standard deviations away I need to go, I need to multiply that by, well, what is the standard deviation? Is it 10? Is it 100? And this was simply square root of our sample variance over our sample size. Okay. So how do I use this table to find these values, right? Just like we're using the standard normal. So the standard normal distribution was kind of matching up these z values with their corresponding areas in the left tail. This is going to be matching up t values with their corresponding value in the right tail. But the two tables are somewhat flipped because in the standard normal, our z values, we were using the row and column headings, right? And then the numbers in the middle represented those areas in the left tail or probabilities. The t table is exactly the opposite. So the numbers in the middle here represent our t values, and the column headings represent the corresponding areas in the right tail. Okay? So it's kind of everything's flipped now. The column headings no longer are these number of standard deviations the way we need to go. Our column headings are now the probabilities. So you can kind of see the student t table is a little bit limited, right? Because I've only got 6 areas in the tail that I'm looking for. But you'll notice we're using this for confidence intervals. And I said the most common confidence intervals we use are 90, 95, 99%. That would be alphas of 0.1, 0.05, and 0.01. Alpha divided by 2 for those benchmark values will always be the same, right? Alpha is always going to be the same for those confidence levels. So alpha divided by 2 will always be the same. And notice those values are one of the, 3 of the 6 different areas in the tail that the student t table tells me. So I can use this to find this number of standard deviations the way I want to go. All right. And then the only other piece of information I need is, well, what student t distribution am I using? Right. Well, that's based off of our degrees of freedom, which is a sample size minus 1. So the row headings represents what degree of freedom I'm looking at. So let's say I wanted that 0.025 in my tail, and my degrees of freedom was 20. Right. What I would do is say, okay, look, here's my degrees of freedom of 20. The area I wanted in the tail was 0.025. So the number of standard deviations the way I need to go, or the t value that would give me that desired alpha over 2 in the tail, would be 2.086, which kind of lines up with what we were saying before. It's going to have to be larger than the value we would have found if this was a standard normal distribution. Okay. Any questions over anything? Yeah.
How did you figure out why there's the 20?
So there, I was just using that as an example, where the one I had up here on the board, I said, assume that this is the student t distribution for a degrees of freedom of 20, right? So this is going to have to be something like, once I have my sample, I'll know my sample size. So here my sample size would have been what? My degrees of freedom is 20, and the degrees of freedom is just the sample size minus 1. This would be if I had a sample of size 21.
Oh.
Yep. Any other questions? We'll keep moving here. We'll go through some more examples here. But one thing I kind of wanted to point out was if this distribution is getting flatter and flatter, right, for different degrees of freedom, then to get that same area in the tail, I'm going to have to keep going out farther and farther, right? Or that t value is going to keep getting bigger and bigger. So notice, if I want this same area in the tail, let's say 0.025, when my degrees of freedom is really low, I have to go like 12 standard deviations away. Now, as my sample size gets larger and larger, and my degrees of freedom gets larger and larger, notice that value is kind of going down, right? It's getting smaller and smaller. In fact, if I go oops, I forgot I have to rotate this one too. So there's 2 pages to this. So if I keep going all the way down, notice that if I could get a degrees of freedom of infinity, which is theoretical, right? If my sample size is n-1, infinity minus 1 is still infinity. But it's kind of a weird thing to think about. But even notice, even if I can get a sample size of 1,000, right? The value we found from our standard normal distribution was 1.96. Once I get to a sample size of 1,000, I'm almost there, right? That student t distribution is getting closer and closer to looking like the standard normal. So if I, in fact, could have an infinite sample size, I'd find that it was exactly equal to that standard normal distribution. Now, we can't get an infinite sample size, but we can get a really large sample size and get it so it's really, really close to a standard normal, right? But if we're dealing with smaller sample sizes, right, that's kind of out the window. This is why we have the table. And for these lower degrees of freedom, we can kind of find the t-values that would give us that desired alpha over 2 on either side of our interval. All right, I think I'll work through a problem here and then we'll kind of reconvene to see if we have any questions. So, kind of already set this up for us. Oops, there we go. But our confidence interval equation really doesn't look hardly any different than it did before. It's just that we're using our sample variance instead of the population variance now. And instead of a z-value that gives us alpha over 2 on each side, excuse me, we need to look up the t-value for whatever our degrees of freedom is, right? That gives us alpha over 2. So once we plug our values in, like the very final step, nothing's going to look any different, right? Once I have that t-value, once I have my sample variance, I plug all those values in, it's going to look exactly like what we were doing before, right? It's just that we're now using a different distribution, right? We're using a different table to look up that number of standard deviations the way we need to go. That gives us alpha over 2 on each side. So our steps are going to look exactly the same, right? I shouldn't say exactly, right? But it's very similar, right? So from my sample, calculate a sample mean, find my sample size, and now instead of having a known population variance, I calculate my sample variance. I then figure out what level of confidence I'm trying to build this confidence interval for. That tells me what alpha is. Now, looking up that z value becomes looking up the t value. I can calculate the intermediate, I can do this intermediate step where I calculate the sample variance of my sample means. So I just have one value to plug in here. Or if I really wanted to, I could substitute that in and do it all at once. So the process is going to be pretty similar, right? It's just we're using a different distribution. So let's look at a problem, right? I'm going to skip this one because it doesn't have any context to it. And I think I want to start out with what it does. So let's say that the American Medical Association kind of starts out saying that the mean salary for physicians is $175,000. So I mentioned this a little bit last class, but the whole purpose, or I shouldn't say the whole purpose, a major purpose of a confidence interval is to be able to say, well, look, if with 90% confidence, I know the true mean is somewhere between these values, then anything outside that range, I can tell you with 90% confidence, that can't be the true population mean. So this is, we can kind of think about, this is the value that we're going to try to prove or kind of see whether or not it's in our confidence interval. So we take this sample because we don't think, I don't know, we don't think that starting physician salaries are that high. From this sample, we see that the average physician starting salary from these 81 physicians is $160,000. Right? So what did we find from our sample? Well, we have a sample size of 81. We had a sample mean of 160,000. And our sample variance is 324 million. Okay. Notice when you're dealing with things like salary, the variance gets pretty large pretty quick. Okay. So if I wanted to build a confidence interval, right, and I've got kind of my equation down here, I'm just going to start plugging in what I know, right? So I've got 160,000, and I'm going to add and subtract, right? Add to get my upper bound, subtract the margin of error to get my lower bound. Now I don't know what this t-value is yet, right? But what would my degrees of freedom be? Well, that's simply n minus 1, so 80. All right. So my degrees of freedom here is going to be 80. If I want to build, I didn't even tell you. So if alpha is 0.05 here, so 0.05 divided by 2, 0.025. Well, what level of confidence would this correspond to? So remember, alpha represents the percent outside of my interval in decimal form. So if it's 0.05 is outside of my confidence interval, right? 5% will be outside, so 95%. Right? So if I've got alpha represents the decimal form of the percent outside my interval, right? So if I have 0.05 total in my tails, right? Then what would kind of be within this? Well, 0.05 would be 5% outside of my interval, which means I have to have 100%. So 95% would be within my interval. This is the idea. So we can go from the level of confidence to alpha, or we can work backwards. So if we had an alpha of 0.1, that would correspond to a confidence level of what? 90%. So the only other thing we have to do here, and you could calculate this standard deviation of your sample means. That was the square root of your sample variance over your sample size. So you can kind of do this separately, right? Or break this down into an intermediate step. Now notice here when we're dividing by n, right? We're not using the degrees of freedom. We're dividing still by our sample size, okay? So if I do it this way, now I only have one value to plug in here, right? Or I could substitute this all in at once if I really want to. So the only thing left that I need to do is look up that number of standard deviations away I need to go, add degrees of freedom of 80 to get 0.025 in each tail, right? Alpha total is the area in the tails, so alpha over 2 is how much is in each tail. When I look at these values, I don't think there's any I can rule out because actually, no, there is one I can rule out. So which of these could I rule out without even putting it, picking up a calculator? So what should be true about my confidence interval is that my sample statistic, in this case, the sample mean, well, I'm adding and subtracting the same amount to it. So it should be smack dab in the middle of my confidence interval. If I think about these, and I'm looking at my sample mean of 160,000, 160 is a lot closer to 163 than it is to 146. So I can rule C out right away. I think the other three, 160,000 falls exactly in the middle of them. So there's none of those I can rule out, but I could rule out C because I know that my sample mean, I'm adding and subtracting the same amount to it to get my upper and lower bound. It should be smack dab in the middle of my confidence interval. Okay. From here, we're going to go to our T tables. Scroll down here. My degrees of freedom, remember that's what's kind of my row headings there. We had that was 80, right? Now this is where kind of having this in front of you helps because I've got to scroll up now to see, okay, what was the desired area we wanted in each tail? 0.025. So this is another thing. I don't love this student T table for one reason. If you are printing this out, just cross off that little alpha up there. The column heading isn't alpha. The column heading, I think a better way of thinking about it is it's the area in that upper right tail. So when you're using those column headings, you're usually looking up alpha divided by 2, right? So I don't want that to confuse anyone that like, our alpha was 0.05. We're not using this column. These just represent, and kind of notice that lines up with this picture. Oops. The way this table is using alpha is it's just the area in that one tail. Right? So cross that alpha out from the top of this table, if that helps. Think about these column headings is the area you want in the tail, which is alpha over 2 for now. Okay. So 0.025 was that area we want in the tail. We then go down to our degrees of freedom of 80. So that number of standard deviations away we need to go, or our T value here is what? 1.99? Well, now it's just a matter of getting this entered in my calculator, right? I'll got everything I need. I'll add my margin of error to my upper bound. I'll subtract my margin of error to my lower bound. So is it clear how I found that T? Are there any questions over how I found that T value? So all I need is my degrees of freedom. That's my row, right? And then the column is just that area that I wanted in each tail, which, just like the examples we were in before, that's going to be alpha over 2.
But so if we're given a problem like this where we have to find probability instead of a confidence interval, and this gives us the area to the right on that right tail. So we wouldn't, like, let's say we're trying to find the probability of something over a certain value. We wouldn't have to do a 1 minus it anymore. Is that what I'm saying?
Yeah, so we kind of jumped in the gun to what we'll do next week, which is hypothesis testing, and which is for confidence intervals, we're never using we're always using the inverse process, right? Because we're always looking up the area we want in the tail. But you're right, because this distribution is looking at the right side, right? My alpha over 2, I'm always thinking about that's going to be the area on the right side of the distribution. So I no longer, like if I did want to know, I don't know, how many standard deviations away do I need to go to get 0.06 in that upper right? You don't have to do 1 minus anymore because this table isn't looking at the left side of the distribution. It's already looking at the right side, right?
So if we're gonna flip the last bit to do 1 minus that.
Yeah, so now if I did want the probability being less than a certain value, then I would have to do 1 minus. Now, we're not gonna have to do that with confidence intervals, like I said, because we're always just looking up alpha over 2. And, so it's just that we're looking at the other side of the distribution now. You could ask, I won't ask you questions like we were doing before with a sample mean where, you got to use the inverse process, but you could, right? I'm not going to make you do that with a student t distribution though. Any other questions before we keep going here? All right, so I know this is a lot. So where is there we go. So what we did, right, we identified what we were given. So our sample mean, our sample size, and our sample variance, and then we were told out. Right? We then looked up that t-value, right, using that table, degrees of freedom of 80, and that alpha divided by 2 value of 0.025. Excuse me. Then if we wanted to, we could calculate that, use that intermediate step to calculate the standard deviation of my sample means. And now it's a matter of getting everything plugged into that equation. So notice here, I could do this all at once, or because I did this ahead of time, I really just have one value to plug in here. And I also kind of wrote this a little bit differently to show, the square root of the variance over the sample size, because I'm taking the square root of the square, would be the same as the standard deviation divided by the square root of the sample size. So that was something we kind of used, right? I showed you for the earlier confidence intervals as well. I wanted to put both of those forms up there so you can see you could do that in this case as well. So if you're only given the, if you only had the sample standard deviation given to you, it'd probably be easier to use this formula to calculate your standard deviation of sample means as opposed to using that. So I've got my confidence interval. I want to focus on interpretation here. So I want you guys to be able to come up with these when it comes to the exam, which I'll kind of talk a little bit about at the end of class. We might need to do some interpretation as well. Right? So I've got my lower and my upper bound here is 156, I'm gonna kind of round here, to about 164,000. Right? So with 95% confidence, right, I can say that the true population mean based off the sample mean I saw is somewhere in this range of values. So if I go back and think about the American Medical Association telling me that the average starting salary is 175, well, I could go to them and say, look, I don't know what you're basing this off of, but based off the sample that I took, that I believe is unbiased, there's a 95% chance that the value you're putting out there is not true. In fact, the true value is significantly lower than that, right? At the very best, right, it's 11,000 below that. Any questions before we keep moving out? Do another example here. And then I think I'll show you how to do this in Excel. It's really going to be exactly what we did before in Excel. It's just that we're going to have to use a different distribution. So we can't use the norm.s, .i and b function to find that z value that corresponds to alpha over 2. We're going to have to use something else different. So let's go back. I'll do the example just to put some different numbers. That wasn't as interesting because it didn't have a context to it. Oh, where did I go? Did I go back too far? There we go. This doesn't have any context to it, but just getting some more practice looking up these t values. Let's say I start out with a sample where I've got a sample size of 36. And I've got a sample variance of 324. So sample size 36, sample variance of 324, and the sample mean I calculate is 9. Okay. And I want to find a confidence interval for what level? If I've got alpha of 0.01, this would be what level of confidence? 99%, right? 0.01 is the area in my tails. So there's 1% in my tails, which means there's 99% kind of in the middle there or within my confidence interval. So I've got this equation. and I'll just write in here instead of doing the intermediate step. All I'm going to do is start plugging in my values, right? This is, there's not much I can, where is this at? There's not much I can really help you with at this point, right? If you have the formula in front of you, which is on that formula sheet, and you identify what you're given here, it's just going to be a matter of plugging those values in. The only real technique or the only real skill we're trying to build here is then looking up that t-value to find the number of standard deviations away that we need to go to build this confidence interval. So here, what are the two things I'm going to need? My degrees of freedom, and then the formula reminds me, oh, well, I also need the area that I want in each tail, or I've got alpha total in the tails, alpha over 2 in each tail. Right? So what is my degrees of freedom here? So, yeah, so that was just n minus 1. So 36 minus 1 is 35. What will alpha divided by 2 be? 0.005. All right, 0.01 divided by 2, 0.005. So I then go to my table. I've got, this one is a little bit nicer. So I've got degrees of freedom of 35. The area I want in the tail is 0.005. So the t-value that would correspond to that, right? Or the number of standard deviations away I need to go is, and let's see if I can stay on the same row here, 2.724. So if we're thinking about this, right, I need to go 2.724 standard deviations away or above to get my upper bound, and then 2.724 standard deviations below or subtract that margin of error to get my lower bound. At this point, right, it's just a matter of getting this kind of entered into our calculator. Any questions? We take a look at an example in Excel, and I'll kind of do that example up on the board as well, kind of show how we would work through it by hand with the numbers that we have. It's making some sense. No, not at all. Why? Tell me, like, I need questions, right? You can't just say that.
It literally feels like a form right
Okay. So if I had to break this down to its simplest form, right? When I'm thinking about either one of these distributions, right? What we're trying to do is look up how many standard deviations away we need to go. It's almost like if I had a list of all these different z values. So let's say I had a column of these z values. There is a corresponding probability that goes with every single z value. That's all the table's telling me, right? It's telling me that if you look up this value, that matches up, you know, that z value matches up with this probability. You can kind of think about it in general math, like if you've got a bunch of x's and a bunch of y's, and I tell you x, like there's always going to be one corresponding y value on every single line with it. So all we're doing is looking at different z values, right? Going from the smallest to the largest, and we're just getting cumulative probabilities. So we're always getting the area to the left. So these values are always going to be larger as well. And we're just using the table to find what z value gives us that area in the tail that we want. Right? Same thing would apply if I had the t values here. It's just that if I think about like the t values that would correspond to the same probability, I don't know, be something like 2.01, whereas here it might be 1.28, right? So it's just that our t values, right, are going to be a little bit different than our z value when that correspond to that same probability that we want. How else can I think about explaining this?
I guess I get lost when you're plugging everything into the equation.
Okay. So my advice for that, right? Write things out, right? So if I'm writing these out, I mean, I'm giving you the notation on the exam and in the slides and the problem, right? I've got my sample variance. So I've got s squared. I'm just looking where would I plug that in. I'm giving you n, the sample size, right? So if I write it out, sample size is 36, just plugging that in. If I have the sample mean, that's 9. I'm just matching up kind of where what I was given goes into that formula, right? So I think writing out what you're given initially really kind of helps you see like, okay, where are these values going to go, right? And then there, you know, like I said, I think the harder step, that at least I would think, is then looking up that number of standard deviations of where you need to go. So the t value in this case, or before a z value, to get that desired alpha over 2 in each tail.
On the test, or like, we'll have a formula sheet.
Yeah. So before we go into Excel here, if I can get this, there we go. Oh, I thought I had a class pulled up. So I put up this yesterday, which is kind of 2 practice exams with some answers, as well as the formula sheet. So the only thing on there is that you wouldn't recognize is what we're going to cover next week, which is hypothesis testing. So we're going to have that exam, I think, pushing the date for a little bit. It'll be that Monday, the 7th, I believe, is the date. So I'll put an announcement up on Canvas that, you know, got about a little bit more than a week. We'll have one more thing that we're going to cover, and then we'll have that exam on that Monday, right? So I think we'll probably get a little bit of review in next Friday as well, which is kind of why I'm pushing it forward a little bit.
If we do bad on this test, it's not worth as much as the last one, right?
Yeah, you do bad at it, right? So your best kind of exam is weighted the most. So we got 7 minutes. I think we can kind of do this. So I want to make sure you guys can get kind of a pretty good way through that. So I reposted this median rental price in class data set this morning. So I added a new sheet to it. So before, this is all, you know, we had all the work we did for the other 2. That's on this first sheet, which was all these rental prices, right? So I put up another data set that we'll use today to say, okay, look, it's kind of hokey. I was giving you this known population variance, but how did I know that if I don't have population data? So now we'll just say, okay, what if we're just starting out with a sample? We know nothing about the population, which is a little bit more practical. So I found this kind of goofy data set that I thought would just be fun to take a look at, which is on UFO sightings, right? So here, the variable I'm going to use, we're thinking about what's the true population mean for the length of a sighting, right? And this is in seconds. So we can kind of convert that at the end of minutes if we're really interested. You could be not interested in UFOs at all. We can just think about this as what we're going to use to kind of get an example here of building a confidence interval in Excel. So what are the 3 things that we need? Well, we need our sample mean, our sample size, our sample size, or n, and our sample variance, okay? Scroll over here there. So hopefully at this point, these are getting to be kind of old hat. So I'll use my average function of that duration variable to find my sample mean. I'll use my count function of that variable. Remember, control shift or command shift is how I'm selecting that entire column quickly. And then we go back ways, we had that var.s, which would help us calculate that sample variance, okay? So instead of typing this in, one thing that might be easier here is, let's say I just want to look at these confidence levels. I'm going to go back to my other sheet and just copy these, right? So I could type them out again if I really wanted to. Might make easier just to kind of copy paste, okay? So I've got the 3 things that I need here, right? My sample variance, my sample size, and my sample mean. I've got my different alpha values, right? I'm going to build 3 different confidence levels corresponding to different alphas, right? Kind of our benchmark 90, 95, 99%, or alphas of 0.1, 0.05, and 0.01. So the way we set this up before, we broke it down into steps, right? That in order to find my upper and lower bound, I first need to figure out, well, what's the last piece of this equation I need? I need to know how many standard deviations away am I going, or now my t value as opposed to my z value, right? So here, I'm going to try to find my t values, kind of breaking this down in steps, right? So before, to look up alpha over 2 and to find the corresponding z value, we used norm.s.inv and then just told it alpha divided by 2, that area we want in the tail. Here, whoops. We're not using the standard normal distribution anymore. We're using our student t distributions. So instead of norm.s.inv, just t.inv. You're telling it the type of distribution you want and that you're kind of working in the reverse. You're going to give it the area you want in the tail, and it's going to spit out at you that t-value. Now, what area do we want in the tail? Alpha divided by 2. Oops. But notice, I now need a second thing for this equation. So norm.s to INV, I just had to tell it alpha over 2. Problem is, it needs to know what student t distribution am I using. So what is my degrees of freedom, right? Well, my degrees of freedom is simply my sample size minus 1, right? So this is basically going to be what we're doing using the table. It's going to look up alpha over 2, spit out at you the corresponding t-value that gives you alpha over 2 in the tail. And this I don't love, but unlike the physical table, the t.inv function that's built into Excel works the same as the norm.s.inv. So now instead of the area in the upper right tail, it goes back to just like the standard normal distribution in Excel. This is telling it the area in the left tail. So the problem is going to be, it's going to give me the number of standard deviations where I need to go, but it's telling me that the same value I would have found from the table, it's just putting a negative sign in front of it, right? So I just have to remember that when I'm building my upper lower bound, those are already built into my equation. So I don't need that negative sign. So we said an easy way to deal with that is just use that absolute value function, or ABS. This will kind of just give us that number of standard deviations away that we want to go. I could then copy this down. Oops, what happened? Right. Oh, yep. So now that I'm using my sample size, right? Yeah, I do want alpha to update, but I'm always using the same degrees of freedom. So I need to freeze that cell reference. Okay. Now, when I copy this down, hopefully I don't see these errors. Sure enough, it got it kind of working. Running out of time, but I want to make a couple of points. So at this point, it's just like what we did before. It's just using Excel to be our calculator. We're just selecting the cells that have these pieces of information in them. So I won't waste time today doing that. I'll post the completed version so that you can have it as well, but it's exactly what we did for the examples where we had a known population variance. The one thing I did want to point out is these values look really, really similar to the standard normal values. Why are these so close to my standard normal values?
There's such a huge sample size.
Yeah, I got 41,000 as my sample size. So just to kind of prove a point how much these values can change for lower degrees of freedom. Let's say I found the exact same sample mean, variance, everything, but that I only had, I don't know, 50 observations. So now when I hit enter, everything should update because I used cell references. Notice the t-values that would correspond to degrees of freedom of 49, right? 50 minus 1. Notice those change quite a bit. Now these look quite a bit different than my standard normal values. So it doesn't matter what the size of my sample is, as long as I'm kind of telling that t.inv function what my sample is, it's using the right t distribution for me. Okay. Let's see one of those cells again before we kind of get out of here today. So we're getting an announcement up on Canvas. You've got those practice exams. I'd start kind of going over those. I'll also put up a short, what looks like a Connect assignment. It is just meant for practice next week if you want some additional practice problems. It'll have confidence interval stuff on there, and then some problems on what we're going to cover next week, which is hypothesis testing. So it is not worth any points. I have to give it a due date, but I'll put the due date as the date we're taking the exam so that you'll kind of have access to that. And if you want to kind of work on those for additional practice problems next week. Okay.
But it's different from the Excel assignments next Friday.
Yeah, so the Excel assignment is due next Friday. This other one, it's not an actual assignment. It's like, I'll probably label it like practice assignment or practice problems. Yep, it's just for getting some additional problems up there. Yep. All right. All right, so I will see you guys on Monday. We will do hypothesis testing. It'll be very important to see that concept introduced, so I highly suggest making sure that you're here and awake and ready to go.